Yeah.
And you'll see another one in there too as well, from a historical event actually. This is probably the Japan event, the Tohoku 2011, because it starts from Japan.
It's terrible for me to ask, but I always pronounce your last name Olugboji.
Perfect. You're very well done.
Are you sure?
Yep, 100%. Yeah.
Cool. It's not terrible for me to ask, but it's terrible for me to ask this.
It's okay.
But if I'm standing up in front here,
And I put like a little cheat sheet there too.
Oh, there it is.
Yeah.
Oh, no. Yeah, that is it.
And you guys all meet up together? Yeah.
Yeah.
We're all sort of like walking together.
Yeah, I'm ready.
Good afternoon, everyone. It's my pleasure to welcome you all to this afternoon's seminar from the Department of Earth and Environmental Sciences as part of our Meliora weekend program. My name is John Kessler. I'm a professor and chair in the Department of Earth and Environmental Sciences, and it's my pleasure to introduce today's seminar speaker. Before I do that, though, I noticed some new faces that I'm not as familiar with, and so I wanted to just take literally 2 minutes to give a very broad brush overview of the Earth and Environmental Sciences Department. EES was actually founded in 1888 by Herman Fairchild. We started as the Geology Department, and since then have grown to include planetary sciences, ocean sciences, and atmospheric sciences. If you come over to our department after this seminar, which I hope that you will, we have a nice reception set up, you'll see that a lot of the research and some of the educational themes are actually cross-cutting across a lot of these disciplines for a very holistic view of our system. Now, EES has two profound academic interests, let's say, that I think are going to be prominent for years to come. Number one is climate science. And our fundamental understanding of our climate system, come on in, please. You're welcome, come on in. The fundamental understanding of our climate system, especially in the context of a warming world, is not only one of the highest priority questions that geoscientists research, but also for humankind as well. The second research and academic interest that we have is planetary science. And included in the core of that is the continued study of our own planet as the model of habitability. And so those two, I think, academic interests really drive who we are. And planetary science as well being, let's say, in the golden age of planetary exploration that we currently see ourselves in. And now that's all well and good, but if I'm asked to ask myself, if somebody is to ask me what makes EES so special, what makes us different than other geosciences departments, what makes me so interested and excited, I can really say, to come to work every day, it's because of the people that I get to work with. The individuals, the faculty who work in this department have a love, a spark in them for geoscience that is really unprecedented. I think that drives the work that they do, and they're so good at kindling that same spark as they work with students or other individuals next to them, and kindling that same spark in them. Now, one of our faculty members, Professor Tolulope Olugboji, who will be presenting today's seminar, not only has just that spark, he has what I would classify as a raging fire for geoscience inside of him. I think you're going to see a lot of that today. Tolu did his graduate work at Yale University. He got his master's and his PhD at Yale. He spent a few years at the University of Maryland doing postdoctoral research before we were lucky enough to hire him in 2018 as an assistant professor. Now, Tolu is a computational geophysicist and a seismologist, and he uses ground vibrations from seismic sensors across the globe and high-performance computing and machine learning to actually image what's going on below the surface of our planet for increased earthquake prediction. Okay.
Indeed, perfect, yeah.
Great.
Yeah.
So, of course, he will do a much better job at describing this than I will. So I think the best thing that I can do is just to welcome him up to the stage right now. So please join me in welcoming Professor Tolulope Olugboji.
Thank you very much,
And he
John.
also, I will say, reminded me to remind you to actually take out your cell phones, which is a rare thing to do at an event like this. So
Exactly.
if you have one, please get them ready, because
Yeah.
I think there's going to be some interactive components.
Indeed. So pull out your cell phones. Normally you come to a lecture by a professor and the professor says, put away your cell phones. Focus on me. Not at all. Pull out your cell phones. Go to that QR page, a couple of polls in today's lecture. And to start off, I'll just ask, what comes to mind when you think of the title of today's talk? And just literally text in. You can just say, it's me, just tired, bored out of my mind. No profanities, please. I'll give you some time to do that. Okay. And I'll give you'll get many more opportunities to interact with me, with yourselves, with the material I'm delivering today through this medium. Thoughts? Oh, I have Evan here. Evan is my PhD student. He's an unofficial kind of teaching or lecturer assistant for today. If you have any problems with the poll at all, just raise your hand. He'll get to you. He'll help you make the most of today's technology. Okay, let me look at what you guys are saying. No math. Nobody wants to see any math. Professor Dr. O, which some of my students call me because my last name is a mouthful, Dr. O likes math a lot. We do not want to see math in today's lecture. Can I or can I not guarantee that there will be any math in today's lecture? No comments. Okay, so let's start today. Hello, everyone. The story I'll tell you today is about the science and history of earthquakes, nuclear bombs, and Earth's anatomy. The animation on the left shows an earthquake, right? And an associated tsunami. It's a violent, destructive shaking that happens from time to time on our planet's surface. And seismology, which is derived from a Greek word seismos, to shake, agitate, and shiver, and logy, the study of this said shaking, is the science that explains such violent shaking and other connected phenomena, plate tectonics, volcanoes, earth structure. And on first glance at the title, one might ask, what is the connection between these three topics? Is there any connection between these three topics? The next 40 minutes will address this. My lecture will be in three parts. Part one, I will look very closely at the history of earthquakes, milestones, the theory, the technology of this emerging science. In part two, I'll describe how the Cold War advances the science of forensic and planetary seismology. And finally, I'll come home to the University of Rochester and explore all the exciting research that's being conducted here at the University of Rochester. So welcome, and let's get started on the science of forensic and planetary seismology. So when an earthquake happens in the news, what do we expect? A great earthquake, what do we expect? I can still remember two great earthquakes that happened in my lifetime, Indonesia and Japan. The images you're looking at here evoke scenes of utter chaos and destruction. On the left, we see an entire city submerged by a tsunami. Death tolls, 250,000 people dead. In Japan, it was not so much the earthquake that caused the most damage, but the tsunami. The Japanese are kind of used to earthquakes, but they did not predict the tsunami. They could not have predicted the tsunami that happened. Amongst other things, in addition to loss of lives, it led to the meltdown of the nuclear reactor at the Fukushima power plant. So, earthquakes cause the ground beneath us to shake violently. It destroys homes. It leads to large human casualties. And when they happen, as they happen often in Earth's history, they lay waste to cities, sometimes altering the trajectory of human history. So I'm just showing here a timeline, 1900 to present day, of great earthquakes that happened in human history. So you might not remember a great earthquake, but I guarantee you, if you live long and walk on this planet, you probably experience one before you no longer walk the planet. Okay. So speaking of history, one important earthquake in human history, I would argue, is the Great Lisbon Earthquake of November 1, 1755. And I'll tell you why it is important. It helped move humanity towards a scientific understanding of earthquakes. So on this slide, you see a 19th century illustration of the catastrophic devastation of the prosperous city of a once vast European empire. If I could paint a picture for you, I wasn't there, accounts. The earthquake happens at dawn on a Sunday. The city is a religious Catholic city. Many are gathered in the churches celebrating All Saints' Day. I'm Christian. All Saints is November 1. You know it as the day before Halloween, or Hallows Eve Day. Around 9:30 a.m., a violent shaking causes church bells to ring in unison. Some people recall a horrible subterranean noise right before the ground beneath them begins to shake violently for almost 6 minutes, causing church cathedrals to crumble and entire neighborhoods to be decimated. Within the hour, as you see in this image, a 6-meter tsunami plows into the waterfront, killing hundreds who have gathered there for safety. Another thing about great earthquakes, if you're near the coast, run the opposite way, not towards water. And then the final blow hits. Fire ravages the whole city, set up by candles and fireplaces, adding to the apocalyptic scene of destruction. Falling buildings, tidal waves, and raging fire. So two views emerge as leading thinkers of the Enlightenment wrestled with this catastrophic event. One view, no surprise, was that this was an act of divine punishment for the people's sins. The other view, because now we're in the Enlightenment, says that the event is just a result of long natural chain of interactions between matter and energy. Not as sophisticated as that, but that was the view. So nature is uninterested and indifferent to human welfare. So while the 18th century priests and philosophers and poets argued about the Lisbon earthquake, the cause and the meaning of the earthquake, little progress was made because there was no seismic instrument in 1755. The closest to a scientific approach was described in his monograph by John Mitchell, professor of geology at Cambridge University, England. His idea was simple and yet profound. It captures the main ideas that we have in today. So the idea goes like this. Earthquakes propagate outward like waves, So if you can identify the direction of wave propagation at different locations in some area, plot those directions as lines, and find the point of intersection of these lines on a map, you should be able to identify the location of the event. In this way, I argue Mitchell, I don't know, was an early father of seismology, correctly confirming what you see in this animation. This is a reconstruction by NOAA using all the data they had from 1755, showing what happened in 1755. So what you see is the earthquake happening in the Atlantic. The tsunami, because it displaced the seafloor, it displaced the water violently, and the water waves propagate outwards. And as the water wave reached the coast, you see those colors, blue, yellow, red, those water waves come crashing in. And it turns out most of the time it's the tsunami that causes a lot of damage. Red and deep red means severe hazard. If they had this information, they would have evacuated the entire waterfront. Wave heights reaching almost 10 feet. So the lesson we learned here from Lisbon is that scientific progress rests on facts, measurements, and experiments much more than speculation. Now, speculation is great. In fact, we're paid to speculate, scientists are. But your speculation should be grounded in empirical evidence. And how do we get empirical evidence of the shaking of the ground? Guess what? Chinese were at it 132 BC. And so here are two concepts of an early device to measure earthquakes. Now, the device is called seismometer. Seismos, shaking Greek word, meter, measurement of. So we have now a meter stick for measuring seismos, for measuring shaking, seismometer. On the left, you see the 132 BC seismoscope, invented in China. It's got a lot of the important components of a measuring device for shaking. It is ingenious. It tells you the arrival direction of wave propagation, as you can see, by its operation. But I would argue it's an incomplete seismometer. What is missing? It is missing time, amplitude, and a permanent record. Let it be written, let it be done. If it is written, it will be remembered in perpetuity. The perfect seismometer, or the near-perfect seismometer, was invented around the 19th century, and all seismometers have this principle of operation. They are spring mass pendulum devices, where the mass vibrates when the ground does, and an attached drum or recording device that continues to take time, measures the movement of that mass, giving all those components I gave you for a seismometer. Timing, constant rotation of that drum, amplitude, how violently the mass swings, and a permanent record. The shaking of the ground is now permanently recorded on the paper. With such a device, the first seismogram was recorded, as you see in the image on the left, by no other than a German. My wife is part German, and I asked her to help me pronounce this name, Ernst von Räuber-Paschwitz. April 17, 1889. And everybody applauds. Observational seismology is born. Happy birthday. So from then until now, seismology continues to play a unique role in forecasting the shaking intensity and the space-time evolution of earthquakes, as is illustrated in the simulation on the left, where you have the 1980 Loma Prieta earthquake, showing how shaking intensity propagates in time from the epicenter on a fault in San Andreas in San Francisco, California, USA. The better we understand how the ground shakes during an earthquake, the better we can design buildings and infrastructure that can withstand violent shaking. And although we cannot yet predict when an earthquake will actually happen to the minute, we can forecast. We can forecast where they will happen. We can forecast how the waves will propagate, and we can forecast how destruction will proceed. And so we can design things like rapid early warning systems, and all this technology helps us to transcend the fear of nature's fury. And so that's history. We come to the theory of earthquakes. Math or no math? That is the question. So this is a history of wave theory. And since that is essentially what the phenomenon of earthquakes is, that is what we will explore. But first, let us now define seismology and the central concepts in seismology. Seismology is the study of elastic waves, i.e. ground vibrations, propagating through any planet's interior, giving the information about the medium of propagation, typically rocks, through which these waves propagate, as well as about the source, what happened at the source, how that source was forced, how it broke, the source that created those waves. Planetary seismology, that's that. Forensic seismology, can we discriminate between natural and unnatural shaking, sanctioned and unsanctioned shaking? Providing evidence to tell when a crime has been committed is the goal of forensic seismology. So the key concepts are waves, propagation, and because it's geology, rocks. So the rocks of our solid Earth are the medium that transmit the shaking of earthquakes as it propagates out. And waves can be classified by the direction in which they propagate relative to the direction the rocks themselves vibrate. So just like sound, just like light, and just like water, waves in the solid Earth behave almost like that. So when you've got sound, the wave is propagating in the same direction the air is vibrating, along the same direction longitudinal. For light and all other electromagnetic waves, the wave propagates transverse, which is just a fancy word for perpendicular. Perpendicular to the direction of vibration of the electrical and magnetic medium. Believe it or not, that is empty space. And for water, it's an interesting type of wave. It's just a surface gravity wave that is a coupling between these two types. So as you look at the water wave vibrating and propagating, you see that the vibration is both longitudinal and transverse to wave propagation. So that's very intriguing, exciting. You can try to wrap your mind around that, but that's the general idea. So inside the solid Earth, we'll see a similar behavior. What we perceive as shaking at the surface is the arrival of a solid Earth vibration that has propagated from the source of an earthquake, traveled through the body of the Earth as compression, shear, and across the surface as a surface wave. So compression, longitudinal like sound, shear, transverse like light, and water wave, surface, Rayleigh waves coupled. These waves provide all the empirical evidence and empirical information we have about the medium through which they propagate, that is our planet's interior, from the crust, which you are all sitting on, all the way into the core of our planet. By the way, much of the beautiful theory of surface waves was worked out by these two handsome scientists before their detection by advanced seismometers. On the left is Sir Love and Lord Rayleigh. Oh, by the way, Love is the other type of surface wave, and its propagation is pure shear vibrations trapped on the surface of the Earth. And I am always trying to publish manuscripts that have love in their title. I haven't succeeded yet. The last time I tried, it was something like looking for love across the Hawaiian swell. Haven't found it yet. Okay, let's pause and let's ask a question. Pull out your phones and see if you can answer this question. Which of these vibrations is most likely to cause this building to have collapsed? Or if you cannot find the QR code, there it is. You'll see the question on your phone when you get to it. If you need any help, trusty old Evan is here. He'll give you help. So you literally can just pull up your phone and bam, you're in it. How many of you are in there? Okay, so we can start looking at your responses. There we go. The class is split. So now is where I tell you to talk to your neighbor, if you have a neighbor and you care about your neighbor. And you try to convince them of your answer. And we wait a little bit more, 44-second countdown. So the first A is compression, B is Rayleigh, and C is love. And are we out of time? Is it locked now? It's still running? If you were an earthquake wave and you were given the power to push this building, how would you push it if you wanted it to collapse? That's a question you want to be thinking. I see you, yeah, I see you. Okay, let's give the class 30 more seconds to engage. Did I give you only one option? You can't change your mind, can you? No, you can't change your mind. You guys are all locked inside. I'm sorry. Should I give you an opportunity to change your mind? Okay, so let's see what the answer is. Oops, I went too far. Oh, math, no. So the correct answer is love. You do not want to be a building when love comes rolling through. Okay, thank you guys for playing. I like this. It's fun, isn't it? It is. So I did put math in the class. But I promise, it is only so I could say this. Theory is important and beautiful. It tells us that there is surprising harmony between all physical phenomenon. It shrinks the shaking and violent natural phenomenon to simple equations that I can fit on a simple slide like this. Earthquakes are waves, that's what those equations are saying. All destructive vibrations that bring down buildings, bridges, and cause tsunami, all of that can be predicted, described, measured, calculated, and to, most parts managed, if not entirely predictable, at least understood. But this is not a lecture on theory, it's a lecture on history and science. So I will move on. No math, please. From theory to data. And in this case, it's the data that is needed to provide evidence of the source and size of planetary shaking vibrations. Evidence which is necessary to validate the causal theory of earthquakes. And since earthquakes are a planet-wide phenomenon, it will make perfect sense that we need a global collection of stations, a global seismic network. And if I said this network was constructed because of pure interest in science, I would be entirely, completely wrong. Like most things, the story is complicated. History is complicated. History is an intricate connection between scientific progress and sometimes humanity's self-destruction, which is war. So sometimes scientific progress leads to war, fuels war, and sometimes vice versa. War can lead to scientific progress. I'm not arguing for war, I'm just stating the obvious. So the seismic network that provided this data was furnished because the Second World War was fought and decisively won by the United States, obviously, and its allies because of a most terrible bomb, right? So at the end of the Second World War, the USA had dropped the 2 bombs, ended the war, and only for a brief time did it have exclusive rights to the bomb. Almost immediately after, 2 or so years, the Soviet Union gained, and other countries gained nuclear capabilities. And then a passive-aggressive stance ensued, where the 2 great nuclear powers, the USA and the Soviet Union, tested weapons without an outright confrontation, thankfully. And this is what we call the Cold War. And this animation illustrates some of the brinkmanship of that era. Bombs being tested on our planet just for the sake of saying, I got the bigger, better bomb. It reached its climax in the 60s as both countries tested bigger bombs and amassed large amounts of nuclear stockpiles. It became clear that mutual assured destruction would be the effect if either country attempted to use such bombs in an actual Third World War. So eventually, they came to the table and they said, no more. But if you're gonna impose a ban, you want to ensure that people keep the ban. So to enforce the ban, technology had to be invented, and hence seismology. So to facilitate a means for enforcing the ban on testing nuclear weapons, the worldwide standardized seismic network, which is what you see on the top right there, was deployed. And that's the era of forensic seismology. It's built, in part, to make sure that countries possessing nuclear bombs never use them in an actual confrontation. And you see the space-time evolution of that, of the number of stations. That's that blue line in that curve. It literally follows the testing evolution. The peak as more bombs, more sensors, and eventually as countries began to sign the treaty and ratify the treaty, it comes down. Eventually, the Cold War ends due to other complex factors, but we eventually got ourselves a worldwide seismic network. The global seismic network, which is that red iris GSN for global seismic network, and the worldwide seismic network are the 2 networks that simultaneously rapidly advance the field of solid earth science. So one can argue war advanced science. Science in the service of national defense became national defense in the service of science. So here's what a seismic station or seismic stations look like in different era in the 20th century, last century. At the start of the last century, you see here, there on the left, a purely mechanical seismometer located in Croatia. It is recording the Italian earthquake on a smoked paper. And if you were to read the most advanced papers of the time, it probably was written by someone from that era. In fact, we get a tongue twister in geophysics called the Mohorovičić discontinuity because a Croatian seismologist probably detected it first. Okay, if you want to detect a boundary, you want to do science at University of Rochester, and you get a boundary named after you. Well, but midway into the century, we transitioned from purely mechanical devices to electromechanical devices. So there in 1961 is what one station looked like, one worldwide standardized seismic network station looked like. That's one of the seismometers used to silence bombs, to ensure that nobody's setting up bombs. In fact, that is the seismometer one of the seismometers in the basement of Hutchison Hall. So we've got a grandfathered seismometer. If you go into the building, you'll see the recording device as you walk into the front door. And then a few decades later, we move from the worldwide standardized seismic network to the global seismic network, which marks the end of the Cold War. We enter into a digital era complex feedback electronics, real-time satellite altimetry, global position for timing. This provides the unprecedented global coverage of the 2004 Indonesia earthquake. And the seismic records you're seeing above that sensor, that 1980 plus GSN STS2 sensor, is the recording of the earthquake made possible by the GSN stations. So with such a global network and sophisticated earthquake location and source characterization techniques, seismologists can provide maps like those on the left, bottom left. And these maps begin to help us answer those important questions about earthquakes. The where of earthquakes, the how of earthquakes, and the why of earthquakes. Just looking at that map provides all the information. You don't need to be a rocket scientist, like, oh, but boom, that's what's happening. So where? Those are linear boundaries marking the boundaries of plates. That is, in large part, where earthquakes will happen. Pause. Ask yourself now, where do I want to build my next home? Close to the boundaries? Probably not. It turns out, though, that close to the boundaries are the prettiest landscapes. So unfortunately, you can't eat your cake. You can't eat your boundary and have it, I don't know, whatever, bad joke. But how? How do earthquakes happen? They happen because there's a rapid release in stress, and they're modeled as force couples. Why? Why do earthquakes happen? They happen because plates move. They get stuck. They accumulate stress. And when the earthquake happens, you have a release, a rapid release of stress. The plates get unstuck, violent shaking as that concentrated energy is released in concentrated time. So the picture that I showed there in the bottom left was a picture, if you see the time history on the top left, going from 900 to 200 and present day, literally probably yesterday when I downloaded that figure, is a picture that has slowly and gradually evolved. You see that spike in counts of earthquakes around 1960. What happened in 1960? Anybody?
World War.
The World War Standardized Seismic Network. And as you get those sensors in, boom, you get to see magnitude 6 events, magnitude 5 events. You begin to put in the space-time picture of where earthquakes are happening. By 1980, the story is done. All the tenured professors at the top Ivy League school that did not believe the theory of plate tectonics were silenced. Evidence, facts, data, seismology. And so there then became the governing, organizing theory of the solid earth, plate tectonics. Okay. So the global data set of ground vibrations provide not just evidence for the causal theory of earthquakes, it also allows us to see inside our planet. And here's an example of how it is done. On the right, on the left, a beautiful picture that looks like a rainbow color, is a derivative picture of all the vibrations that have rattled through our planet. And just like light, at different wavelengths travel to our telescopes, bringing information and news about stars and galaxies and gravitational singularities called black holes. The picture here shows the story from waves. Different types of wavelengths, different types of vibrations, revealing the heating structure of our planet's interior. So every vertical strip through that rainbow diagram is a collection of seismograms, right? A seismograms collected from those 1, 2, 3, 4, 5, 6 stations as the earthquake in Alaska propagates, crisscrossing the planet. So I'll probably go again and show you what's going on. Let's see if I can get it to work. Well, the earthquake happened, the waves radiated, probably on the surface of the earth, crisscrossing through the entire body of the earth. Each of those seismograms from each of those stations, you add them up together, and you put them into that image on the left. So if I was to run my mouse I'm at 90 degrees. That is a station located 90 degrees. The station doesn't know an earthquake has happened 90 degrees away. It's dark, there's no vibration. And then 10 minutes later, blue, a wave comes in, propagated through the body of the earth. A few minutes later, another wave comes through, shear. A few minutes later, another wave comes through, shear, bouncing a couple times, and on and on and on, until you get a complete, comprehensive picture of our planet's interior. Okay, enough. Let's do another quiz. And that gives me time to drink water. So, you are somewhere around 90 degrees, an earthquake has happened, identify the arrival of the surface wave. If you can find the QR code, that is it. Don't worry, the questions are still online on your phone. Back to the question, which is another bonus question, I guess. Have you all answered that other question? Or should I go back to it? Back to it, I can see, okay, let's go back to the other question. Identify the arrival of the surface wave. And the answer is, I see class is split again. But how could you have known? I guess you couldn't have really known, except you paid attention to that animation. But the answer is right around the last one to arrive is a surface wave. So that actually explains why sometimes people will hear a kind of visible sound before destruction comes rolling along. Because the sound they hear is probably that P wave coming in, boom. And then all of a sudden they're shocked, and then the earth begins to vibrate at this very low frequency as the surface wave comes rolling through. And that can be unnerving. I've not been through it, but I've seen people kind of like freak out and try to hug the ground. How many of you have been in an earthquake before? There a lot of the class. Okay, good. Okay, so for a bonus question, which is the fastest? And can you outrun a surface wave? So that's me in a car. Can I, in my car, outrun a surface wave? Can I, on my bike, outrun a surface wave? Is the surface wave faster than International Space Station, or vice versa? And for numbers that can help you, 120 degrees is about 8,000 miles, and it takes about an hour for the surface wave to travel from the earthquake all the way to 120 degrees, 8,000 miles out. The International Space Station is 16,000 miles per hour. I've essentially given away the answer. Some people believe I'm Superman. Thank you, guys. I cannot actually outrun a surface wave. It is pretty fast, but not faster than International Space Station. Okay, so you guys are kind of clued in. So piecing together the timing of all these different phases, as shown on the left, you've got all these waves coming through, compression, shear, compression, converting to reflection as it bounces off the mantle and the core. All that information, you gather all these different phases. They've got fancy names, P diff, S diff, SS. Piece together the timing, and you solve for the velocity. You begin to create a map of, in this case, the radial structure of the Earth. So you may notice on the right of that kind of cutout of the Earth is the speed of the wave, and it goes all the way to 0 in the outer core. And that's the distinct evidence, proof that the outer core is essentially liquid. It's convecting superheated metallic fluid, and it is indeed the source of magnetic field that acts as a shield against harmful charged radiation. Seismology providing irrefutable evidence that, in fact, what's going on deep under our feet is creating protection right above our heads. Also kind of shows the interesting, intricate connections of Earth's systems. So together with two-dimensional mapping of source and receiver geometry on the surface, and sophisticated image reconstruction techniques like you'd have when you're going to get an X-ray or an MRI or an ultrasound scan, we get a full three-dimensional tomographic picture of our entire planet. So a tomos is just a slice, and you get multiple slices proceeding from the surface into the Earth. And it shows also interesting dynamics inside our planet, sometimes also connected to dynamics on the surface of the planet. And I can go on another lecture about that as well, but I wouldn't do that. I'll move along. And so this marks the end of history and overview. In the next few minutes, I'm looking at my time there, I will describe very quickly some of the exciting science being conducted here in the Seismology and Computational Geophysics Lab at UR. We call ourselves UR Seismo. But the key themes are there: Africa, machine learning for Earth imaging, signal processing with noisy ocean bottom seismometers, and obviously Earth imaging with continent-wide earthquake seismic telescopes, earthscopes. And this is team science. This is the rock star of the production. These are the rock stars of the production. Now, here's the team and the projects they are working on. Smart students doing creative work, helping us, when I say us, the community, the scientific community, to understand our planet's structure. So Legray and Zue work on extracting surface waves and understanding earthquakes from pure background vibrations, helping us to understand Africa's subsurface. Zhu and Hennings are computer and machine learning majors, experts, who train computers to build smart images with massive computational power. I used to lose sleepless nights until I had Zhu and Hennings join the team. Zhang, Evan here, Carr, and Lu are working on resurrecting from the dead seismic signals buried in ocean noise. And Bao Wei, he makes sure the entire empire functions. He keeps the computers humming along. He's like a musical conductor, making sure the software and computer work together in harmony. Without Bao Wei, we can't do what we do in our lab. So to understand the fundamentals of the research in our group, it is important to revisit the concept of a seismic recording. So the image you're looking at on the left, and it's running like an animation, shows one such seismic recording. That is a 3-hour recording following that Indonesian earthquake I told you about, the magnitude 9 event. That earthquake, this recording, is being made at the British Ocean Island Station. And like a good vinyl turntable, you can see, and sometimes even if I put it into sound, I don't have the sound here, hear the waves generated. I'll play the animation again, and I'll talk through what you're seeing. So you have that purple line, which is like the spindle on your turntable running through. When the waves arrive, you see the change in waveform shape. And below the same signal is a time frequency components. So just like a prism will split light into its various colors, that time frequency plot is splitting the ground vibration into the different pitch components, the different frequency components of the sound of an earthquake. Warm colors, loud sound. Cool colors, no sound. Before an earthquake, peace and quiet. Silence. Now you gotta use your imagination. Low frequency boom when the earthquake happens. See the warm colors at low frequency. The earthquake has arrived at the island. Silence. A high frequency bang, boom, as the next wave comes in. Some silence. And then crackle as other waves come rolling through. Much of the work done in our group involves separating the signals from silence, especially separating signals from noise when the noise is not what we want to see. And on the right there is illustrated some of the challenges of doing that. Same time frequency representation, 11 days of recording at the Dominican Republic in the last days of August all through September 9, 5 years ago, 2017. So from the top to bottom, you see the difference between human-generated ground vibrations and all the Earth is doing. See that red line at around 5 to 10 hertz, 5 to 10 cycles per second? That is a pump just doing its thing every day, all day. Anthropogenic human sources of ground vibration. And then as you scan down, you get into the field of blue. And you scan down, you get into what the solid Earth is doing. In this case, the oceans and the atmosphere is coupled with the solid Earth. So you see the signature right there, right, of the Hurricane Irma, rolling through, stirring up low-pitch sound, increasing persistent microseismic energy. Wow, microseismic energy actually turns out is useful to image the solid Earth. In the background of that time frequency plot, all those like vertical lines, right? Those vertical streaks in the time frequency plot. What are those? Those are earthquakes that happen ever so often. You see a magnitude 4.5 Dominican earthquake right around August 29. You see a magnitude 4.3 Haiti earthquake right around September 3rd. And then you see the big whopper, the magnitude 8.1 Mexico earthquake right around September 8th. Dominica, Haiti, Mexico. And here's an example of the work being done by Legree, who is trying to understand how the Earth moves during an earthquake in the West African country of Guinea. Who would have known? Earthquakes in Africa? I thought there were no plate boundaries. Again, you see that signal in time, top left right there, the raw waveforms. In the bottom there, the time frequency representation again. And Legree is doing painstaking work using both representation to extract the distinct seismic phases from that time frequency plot, as you see in those little bars. And then in the bottom, he begins to generate computational simulations in such a way to try to match the different models of how the Earth might have moved during that 2021 earthquake. And as you see in the top right, those little balls, they're actually called beach balls, is a representation of actually how the Earth moves. So Legree tries multiple different combinations, and somewhere around 14 kilometers, he's confident that that is the depth at which the earthquake has occurred. In Guinea, West Africa, the ground has moved because of a pushing and a shearing motion in a particular orientation to generate that earthquake. No fault at the surface, but because of spectacular work, we can reconstruct things like that. Here's an example of work done by Zoe. She takes continuous recording from 2 stations. She runs an algorithm that transforms those recordings into another recording called a cross-correlation. The physics of the solid Earth response says, if you create background stochastic long-term pressure fluctuations in the ocean, that vibration will couple with the Earth, generate a surface wave, and you can extract those surface waves. And that's exactly what Zoe has done in those 2 plots there. That is what Africa's Rayleigh waves and Love wave look like when you extract them from sound first ever stuff like that across the entire continent. So she's done that on the catalog of the entire station pairs in and around Africa. I feel like really cool. I'm proud to have done that, and Zoe to have done that with us. Oh, by the way, she's an undergrad who is finally now graduate. She's been working for 2 years. Probably shelter, she's gonna get another publication soon. I just love kind of working with students. It's kind of fun. So from many of these two-station measurements, 10,000 to be exact, and using sophisticated probabilistic imaging techniques as shown in this animation, CU and other interns in the lab have constructed maps of how fast these radiant love surface waves travel across the entire continent. And that's what that simulation is showing. On the left, you do this kind of guess and check probabilistic thing. And on the right, on the right, you do this guess and check probabilistic thing. And on the left, out pops the map. And you've got some error maps as well. And I say out pops the map, but it's 300 computational hours later, 3 months, and see you pulling out a hair. And you get maps like this. And these maps are cool because of other things, but in addition for me is it gives us unprecedented view of part of the world that I am from. And that rarely happens. That rarely happens. You rarely get to say, you know, that's where I'm from. That's where I'm from, where I was born, and I can tell you exactly how fast the wave speeds travel in that part of the world. I'm like, okay. So another cool research by Evan here, and it actually borrows from early forensic seismology work, gets to use signal processing techniques to separate solid earth signals from reverberations of those waves as they resonate within ocean layers or within ice structures, glaciers. And if you know anything about the planet is 60% water and a bunch of ice. If you want to see the solid earth, you have to contend with this problem. And contend, Evan did, and win after contention, Evan did. I sound like, what's this guy? Yoda? Okay, so we start with a signal on the left, top left there. We model the signal of the earthquake on the left as being echoed in time n times, multiple times. And this is exactly what that signal will look like if you repeat it in time multiple times, if you create it as an echo. With the autocorrelation of that signal, you can model the reverberation, you can detect it, estimate it, and use the information from that autocorrelation, these parameters here, R naught and tau, to build a filter in the frequency domain and wipe out the reverberation. Essentially silence the echoes and begin to listen to the solid earth beneath. On the far right is another sophisticated technique, borrows from the early days of trying to find the depth of an earthquake, the depth of an earthquake, so that you can tell if the signal you got on your seismometer is actually an earthquake or the Soviet Union. So by just carefully listening to the time the echo arrives, and then converting that time to a depth, you can say, oh, this is just an earthquake, let it go. Or, come on, man, the Soviets are at it. Go send monitors to check things out. And so Evan uses a technique like that to model the echoes and remove it. It turns out technology like this is probably sitting in your smartphone, listening to your sound, extracting interesting sound signatures of your voice, and helping you to tell when a movie you care about is on. Siri, tell me what's that movie you guys all watching now? I don't know, Game of Thrones, I don't know. So I end by thanking everybody who works in my team, past undergrads and postgrads that have made science here at Rochester fun. I encourage interested students, alumni, friends, join us, come see us in our lab, talk to us. When I say us, the students, they'll love to. Join us at UofR Seismo. Start your career at UofR Seismo. Take a course at UofR Seismo. But I hope I have encouraged interest in the exciting fields of natural hazards, seismology, signals, stochastic methods, and earth science. At UofR Seismo, we are joining to contribute to the 300-year-long history of seismology and earth structure. So if you want to learn more, take our